Hey there, science fans! Today, we're diving into the mind-blowing world of Isaac Newton, a super smart dude who lived a long time ago. You know, the guy with the apple and gravity? Newton was a rock star physicist and mathematician. He totally revolutionized our understanding of motion. We're talking about the fundamental laws that govern how stuff moves, from baseballs to planets. Before Newton, people had some wacky ideas about why things moved or didn't move. Newton came along and said, "Hold my apple juice, I've got this." He gave us 3 laws of motion that explained everything. These laws are still used today, centuries later, because they are that awesome. Get ready to have your minds blown. Newton's first law of motion is all about inertia. This fundamental principle of physics tells us that an object at rest will stay at rest, and an object in motion will stay in motion, unless acted upon by an external force. It's a concept that explains so much of what we observe in our everyday lives. Inertia is the tendency of an object to resist changes in motion. This means that if something is not moving, it will not start moving on its own. Conversely, if something is already moving, it won't stop or change direction unless something causes it to do so. This resistance to change is a fundamental property of matter. Think about it this way. A soccer ball just sitting on the grass wants to stay put. It won't roll away on its own because it has inertia. The ball is perfectly content to remain stationary until a force acts upon it. This is why, when you see a soccer ball on the field, it doesn't move unless someone kicks it. It takes a force, like a swift kick, to get it moving. When you kick the ball, your foot applies a force that overcomes the ball's inertia, setting it in motion. The harder you kick, the faster the ball moves. This is a clear demonstration of how inertia works in our daily activities. Similarly, a moving object like a speeding skateboard wants to keep moving at the same speed and in the same direction. The skateboard has inertia, which means it will continue to roll along the pavement until something interferes with its motion. This could be a bump in the road, a curb, or even friction from the ground. It takes a force, like friction or running into a curb, to make it stop or change direction. When the skateboard hits a curb, the force of the impact overcomes its inertia, causing it to stop abruptly. Similarly, friction between the wheels and the pavement gradually slows the skateboard down, eventually bringing it to a halt. Ever been in a car that slammed on its brakes? You jerk forward, right? That's inertia. When the car suddenly stops, your body, which was moving at the same speed as the car, wants to keep moving forward. This is why you feel that jolt when the car comes to an abrupt halt. Your body wants to keep moving forward, even though the car is stopping. This is a perfect example of inertia in action. The car's brakes provide the force needed to stop the vehicle, but your body doesn't have the same force acting on it, so it continues to move forward until something stops it. Thank goodness for seatbelts, which provide the force to keep you safe. Seatbelts are designed to counteract the inertia of your body, holding you in place and preventing you from being thrown forward in the event of a sudden stop. They are a crucial safety feature that helps protect you from injury. So, remember, objects like to keep doing what they're already doing, whether it's sitting still or moving. Inertia is a fundamental concept that helps us understand the behavior of objects in motion and at rest. By recognizing the role of inertia, we can better appreciate the forces at play in our everyday lives and the importance of safety measures like seatbelts. Newton's second law of motion tells us how force, mass, and acceleration are all related. This fundamental principle of physics is crucial for understanding how objects move and interact with each other. Whether you're pushing a shopping cart, driving a car, or launching a rocket, Newton's second law is at play. It's like a recipe for motion. Just as a recipe combines ingredients in specific proportions to create a dish, Newton's second law combines force, mass, and acceleration to describe motion. Each component plays a vital role, and changing one can significantly affect the outcome. The formula is F equals ma. This simple yet powerful equation encapsulates the relationship between force, mass, and acceleration. It tells us that the force applied to an object is equal to the mass of the object multiplied by its acceleration. F stands for force, which is any push or pull on an object. Force can come from various sources, such as gravity, friction, or a person pushing or pulling an object. It's the driving factor that causes an object to move or change its motion. M stands for mass, which is the amount of matter in an object. Mass is a measure of an object's resistance to acceleration when a force is applied. The more mass an object has, the more force is needed to change its motion. A stands for acceleration, which is the rate of change of an object's velocity, speed and direction. Acceleration occurs when an object speeds up, slows down, or changes direction. It's a key concept in understanding how objects move. So, the more force you apply to an object, the faster it will accelerate. This is why athletes train to increase their strength. More force means they can accelerate faster and perform better in their sports. And the more massive an object is, the more force you need to accelerate it at the same rate. This is why lifting heavy weights requires more effort than lifting lighter ones. The mass of the object directly impacts the amount of force needed to move it. Imagine pushing a shopping cart. When the cart is empty, it moves easily with a small amount of force. But as you add more items to the cart, it becomes heavier and requires more force to push. It takes more force to push a full cart than an empty one, right? This is a perfect example of how mass affects the force needed to accelerate an object. The full cart has more mass, so you need to apply more force to move it. That's because the full cart has more mass. The increased mass means that the cart resists changes in its motion more than an empty cart would. This resistance to acceleration is a direct consequence of the cart's mass. Let's do a quick calculation. Understanding the math behind Newton's second law can help us see how these concepts work together in real life. By calculating the acceleration of an object, we can predict how it will move when a certain force is applied. If you apply a force of 10 newtons to a 2-kilogram ball, what will be its acceleration? This is a straightforward example that illustrates how force and mass interact to produce acceleration. Using F equals ma, we can rearrange the formula to solve for acceleration, A equals F divided by m. This rearrangement allows us to isolate acceleration and see how it depends on both force and mass. So A equals 10 newtons divided by 2 kilograms, which is 5 meters per second squared. This calculation shows that the ball will accelerate at a rate of 5 meters per second squared when a force of 10 newtons is applied. That means the ball will accelerate at a rate of 5 meters per second every second. This example helps us visualize how force, mass, and acceleration are interconnected and how they determine the motion of objects in our everyday lives. Section 4, Law number 3, Action and Reaction. It's all about balance. Newton's third law of motion states that for every action there is an equal and opposite reaction. This fundamental principle is a cornerstone of classical mechanics and helps us understand the interactions between objects. It explains why we can walk, drive cars, and even why rockets can travel into space. This means forces always come in pairs. Whenever one object exerts a force on another, the second object exerts a force of equal magnitude but in the opposite direction on the first object. These force pairs are crucial in maintaining the balance and motion we observe in our daily lives. Think about jumping on a trampoline. When you jump, you push down on the trampoline with your legs. This downward force is the action force. You push down on the trampoline with a force, action, and the trampoline pushes back up on you with an equal force, reaction. This reaction force is what propels you into the air, allowing you to experience the joy of bouncing. This upward force propels you into the air. The higher you jump, the greater the forces involved, but they always remain balanced, ensuring you land safely back on the trampoline. Another cool example is a balloon rocket. This simple yet fascinating demonstration vividly illustrates Newton's third law in action. When you release the air in a balloon, it rushes out the back. This escaping air is the action force. This is the action force. The air molecules push against the inside of the balloon, creating a force that propels the air outwards. The reaction force is the air pushing back on the balloon, propelling it forward like a rocket. This is the same principle that allows real rockets to travel through space, where they expel gas out of their engines to move in the opposite direction. Can you think of other examples of action-reaction pairs in everyday life? How about swimming? When you swim, you push the water backward with your arms and legs. You push the water backward with your arms and legs, and the water pushes you forward. This is why you can move through the water efficiently. The harder you push, the faster you go. But the forces always remain balanced, ensuring smooth motion. Walking is another everyday example. When you walk, your foot pushes backward against the ground. The ground in turn pushes your foot forward, allowing you to move ahead. This interaction of forces is what makes walking possible. Even driving a car involves action and reaction forces. The car's tires push backward against the road, and the road pushes the tires forward, propelling the car ahead. This balance of forces ensures that vehicles can move smoothly and efficiently. Birds flying is another fascinating example. When a bird flaps its wings, it pushes air downwards. The air pushes back up on the wings, creating lift and allowing the bird to soar through the sky. This delicate balance of forces enables the bird to navigate and maneuver effortlessly. Rowing a boat also demonstrates Newton's third law. When you row, the oars push the water backward. The water pushes the oars forward, propelling the boat in the opposite direction. This interaction of forces allows you to move the boat efficiently through the water. Even throwing a ball involves action and reaction forces. When you throw a ball, your hand pushes the ball forward. The ball pushes back on your hand with an equal force, allowing it to be propelled through the air. Clapping your hands is a simple yet effective example. When you bring your hands together, they exert forces on each other. These forces are equal in magnitude but opposite in direction, creating the sound of the clap. Pushing a door open is another everyday example. When you push the door, your hand exerts a force on it. The door exerts an equal and opposite force on your hand, allowing it to swing open. Even typing on a keyboard involves action and reaction forces. When you press a key, your finger exerts a force on it. The key exerts an equal and opposite force on your finger, allowing the key to register the input. Playing a musical instrument also demonstrates this principle. When you press a string or key, your finger exerts a force on it. The string or key exerts an equal and opposite force on your finger, producing sound. Shaking hands is another example. When you shake hands, both hands exert forces on each other. These forces are equal in magnitude but opposite in direction, creating the handshake. Opening a bottle involves action and reaction forces as well. When you twist the cap, your hand exerts a force on it. The cap exerts an equal and opposite force on your hand, allowing it to be removed. Pulling a drawer open is another everyday example. When you pull the handle, your hand exerts a force on it. The handle exerts an equal and opposite force on your hand, allowing the drawer to open. Pushing a shopping cart involves action and reaction forces. When you push the cart, your hands exert a force on it. The cart exerts an equal and opposite force on your hands, allowing it to move forward. Using a hammer is another example. When you strike a nail with a hammer, the hammer exerts a force on the nail. The nail exerts an equal and opposite force on the hammer, driving it into the surface. Bouncing a basketball involves action and reaction forces. When you push the ball down, your hand exerts a force on it. The ball exerts an equal and opposite force on your hand, allowing it to bounce back up. Using a seesaw is another example. When you push down on one side, your hand exerts a force on it. The seesaw exerts an equal and opposite force on your hand, allowing it to move up and down. Using a screwdriver involves action and reaction forces. When you turn the screwdriver, your hand exerts a force on it. The screwdriver exerts an equal and opposite force on your hand, allowing it to turn the screw. Using a wrench is another example. When you turn the wrench, your hand exerts a force on it. The wrench exerts an equal and opposite force on your hand, allowing it to turn the bolt. Using a saw involves action and reaction forces. When you push the saw, your hand exerts a force on it. The saw exerts an equal and opposite force on your hand, allowing it to cut through the material. Using a drill is another example. When you push the drill, your hand exerts a force on it. The drill exerts an equal and opposite force on your hand, allowing it to create a hole. Using a paintbrush involves action and reaction forces. When you push the brush, your hand exerts a force on it. The brush exerts an equal and opposite force on your hand, allowing it to apply paint. Using a chisel is another example. When you push the chisel, your hand exerts a force on it. The chisel exerts an equal and opposite force on your hand, allowing it to carve the material. Using a file involves action and reaction forces. When you push the file, your hand exerts a force on it. The file exerts an equal and opposite force on your hand, allowing it to smooth the material. Using a plane is another example. When you push the plane, your hand exerts a force on it. The plane exerts an equal and opposite force on your hand, allowing it to shave the material. Using a lathe involves action and reaction forces. When you push the lathe, your hand exerts a force on it. The lathe exerts an equal and opposite force on your hand, allowing it to shape the material. Using a grinder is another example. When you push the grinder, your hand exerts a force on it. The grinder exerts an equal and opposite force on your hand, allowing it to smooth the material. Using a sander involves action and reaction forces. When you push the sander, your hand exerts a force on it. The sander exerts an equal and opposite force on your hand, allowing it to smooth the material. Using a router is another example. When you push the router, your hand exerts a force on it. The router exerts an equal and opposite force on your hand, allowing it to shape the material. Using a jigsaw involves action and reaction forces. When you push the jigsaw, your hand exerts a force on it. The jigsaw exerts an equal and opposite force on your hand, allowing it to cut through the material. Using a circular saw is another example. When you push the saw, your hand exerts a force on it. The saw exerts an equal and opposite force on your hand, allowing it to cut through the material. Using a table saw involves action and reaction forces. When you push the saw, your hand exerts a force on it. The saw exerts an equal and opposite force on your hand, allowing it to cut through the material. Using a bandsaw is another example. When you push the saw, your hand exerts a force on it. The saw exerts an equal and opposite force on your hand, allowing it to cut through the material. Using a scroll saw involves action and reaction forces. When you push the saw. Section 5. Newton in your life. From cars to rockets, it's all connected. Newton's 3 laws of motion might seem like abstract concepts, but they're constantly at play in our daily lives. From the way cars move to the way rockets launch into space, these laws explain it all. Understanding these laws helps engineers design safer cars, build faster airplanes, and even send spacecraft to explore the cosmos. So the next time you're strapping on your seatbelt, kicking a soccer ball, or watching a rocket launch, remember the genius of Isaac Newton and his 3 laws of motion. They're the key to unlocking the secrets of the universe. And that's it for today's science adventure. Stay curious, my friends.